Welcome back to our last discussion in Chapter 7, where we're going to look at some examples of work as an application of integration. So in the last discussion, we saw that for variable forces, work ends up being the definite integral of force over the distance traveled, where work in general is force times distance. And now we look at some very specific examples with springs and gravity to put this into practice with very specific variable types of forces. And so we'll first look at some Hooke's law examples, or some springs. So Hooke's law deals with the force function for a spring, and we see that the force to compress or stretch a spring x units from natural length is equal to some constant times the amount you've stretched or compressed it. Now, this spring constant varies and depends on the context and the situation and the spring that you're given, and so you're going to have to use the information in the problem to find that constant first, and then you're going to be able to find the amount of work given the scenario that you need to solve. And so if we look at the first example, we're told that 10 newtons of force is required to stretch a spring 5 centimeters from natural length. This information here is going to tell us our K value, our spring constant. Why? Because I'm told a very specific amount of force, 10 newtons. That's equal to, well, I don't know what K is, but I know it's 10 newtons of force to stretch a spring 5 centimeters from natural length. Now, this goes into, before we solve this, I should take note of what are the units of my answer. So if my answer should be in Newton meters, then I would need to make sure to transform 5 centimeters into meters at this point, therefore giving me a spring constant in terms of newtons and meters. If my answer is fine in Newton centimeters, then we can leave it as 5 centimeters, and then just know my answer is in Newton centimeters. And as long as we are consistent throughout, right, we just need to make sure that all the units match, we'll get the appropriate answer. So always be mindful of the correct units to use. In this case, I will leave it as centimeters, everything in newtons and centimeters, so that my answer will be in Newton centimeters. A non-standard unit, but a unit of work nonetheless. And so 10 newtons of force required to stretch a spring 5 centimeters from natural length implies then for this very specific spring, my K is 2, 10 divided by 5. And so the force function for this problem is 2x. So Hooke's law tells me what the force function should be. For this spring, the force function is 2x. That's where I get my K from in the first statement. And then comes the question, how much work is required to stretch the spring 12 centimeters from natural length? Natural length means there's no stretching or compressing. And so if you remember that work is the definite integral of force over the distance traveled, then all we need to do to calculate this work is set up a very simple definite integral. The force function that I integrate is 2x, the force function we're given. And the distance traveled, in this case, the distance stretched or compressed. So if you look at the setup, we are stretching the spring 12 centimeters from natural length. So my upper bound is 12 centimeters of stretching. My lower bound is 0, because there is no stretching, right, from natural length. So no stretching to 12 units of stretching, 12 centimeters. Now we have a very simple integral to take. Antiderivative is x squared from 0 to 12. Gives me 144 minus 0. Or 144, in this case, my units would be Newton centimeters. And so we calculated the work as an integral of force over the distance traveled. And just make sure my units match. I did another example just so that we are careful with this type of scenario, making sure all the units match and everything's consistent. And so in this one, say we have 5 pounds of force is required to compress a 5-foot spring 2 inches. And so we have force equals kx again. So 5 pounds of force is required to stretch a spring 2 inches. Now, I can write 2 here, and that is okay if we want our answer to be in inch pounds. But say, for example, we are required to give my answer in foot pounds. So say I give you the additional requirement answer in foot pounds. Well, at this point, then, I cannot use 2 inches. 5 pounds of force is required to compress a 5-foot spring 2 inches. So what would I need to write here? I would need to convert 2 inches into feet. So 2 inches into feet would be 2/12, right? So there are 12 inches in a foot. So we have 2/12 feet, or 1/6 of a feet. We simplify it. Now, it's very important to realize that this x in Hooke's law is the amount stretched or compressed. It has nothing to do with the length of the spring. And so even though I tell you that it's a 5-foot spring, that bit of information is irrelevant. The x in this variable is just how much it's stretched or compressed. It has nothing to do with the length of the spring. I don't care how long the spring is. I just want to know how much I've compressed it. You notice in this example, in no way did we need to know what the length of the spring was. It wasn't given. It's unnecessary to know. You only needed to know how much it was stretched or compressed from natural length. In the same way here, this bit of information is just there to kind of throw you, right, to make you think, but you don't actually need it right now. We still need to find k though, so I'll multiply both sides by 6. And for our case, k is now 6 times 5, which is 30. And so the force function for this specific spring will be 30x, and will give me my answer in foot-pounds. So now the amount of work done will be the definite integral of the force function, 30x dx, over the amount stretched or compressed. So let's look at the question. How much work is required to compress the spring 10 inches from natural length? And so 0 is my lower bound. I'm not compressing or stretching the spring at all. And I want to compress the spring 10 inches. Now, it is incorrect to write 10 here. If I put 10 here, remember my answers are in feet and pounds. If I put 10 here, this would imply I am compressing this spring 10 feet. I'm doing it 10 inches. And so we would need to convert over here on the side. We would need 10 inches into feet, which would be 10/12 of a foot. If I simplify this fraction, is 5/6. So 0 to 5/6 would be the correct setup. 0 feet of compression to 5/6 a foot of compression, or 10 inches of compression. Now that everything matches up, my answer will be in foot-pounds because I've converted everything into feet. Everything was already in pounds for the force, so we're good. Now we just have a very simple antiderivative to take. 15x squared is x squared over 2, and then 30 and 2 simplify. And then evaluate from 0 to 5/6. Now, plugging 0 in does nothing. Plugging the upper limit in gives me, well, 25 over 6 times 6 is 36. And if I have a calculator, of course, I combine these numbers, but for right now, just understand, right? We can multiply these together if we want. But here is my amount of work done in foot-pounds, the correct unit that I was asked to put it in. And that would calculate it for me, 5 times 25 over 36. So calculating work with springs, I mean, it's a very easy exercise in integration. The integration techniques or things we need to know in terms of integrals are quite simple because the force function we're given is simple, right? The force function is a linear function, so very easy integral to set up and solve. And so we're looking at a little more complicated integral to set up by looking at the other example of varying forces that we talked about, which is gravity. And so now we'll go over to the other board and take a look at an example using gravity. Now, when we use gravity, I have to give you some information because we don't know everything. And if you're not in physics class or you're not an astronomer, you might not know this. But we use some approximations. Of course, we're not going to be very exact because we're more concerned with the math and calculus behind it. For the radius of the Earth, so the distance from me to the center of the Earth, we'll use 4,000 miles. For the radius of the moon, that's, if I'm staying on the moon, the distance from me to the center of the moon would be 1,000 miles we'll use. And the gravity on the moon will be 1/6 the gravity on Earth. So whatever the forces of gravity on Earth, we'll divide that by 6 to get the gravity on the moon. Right? It's less gravity, 1/6 of it, we'll say. Why do I bring this up? Because of the question. So a satellite weighs 10 metric tons on the surface of the Earth. So that's how much it weighs when it sits on the Earth. So that's a weight, and we'll enter in metric ton miles. So we're not concerned with standard units. We'll just leave everything as it is. So it weighs 10 metric tons on the surface of the Earth. So sitting on the Earth, 10 metric tons. Now, how much work is required to propel the satellite 100 miles above the surface of the moon? So we're pretending we're going to take the satellite that we know how much it weighs on Earth, we're going to set it on the surface of the moon, and we're going to propel this 100 miles over the surface of the moon. So we're going to put it into orbit, say, around the moon. All right. So how much work is done in order to be able to do this? Well, we would need to integrate a force function. So first we would need to figure out what the force function is and integrate force over the distance traveled. And so first let's figure out what the force function is. We know that the satellite weighs 10 metric tons on the surface of the Earth. So that's how much it weighs. That's its force on the Earth. Equals, we don't know this constant, so just like we had to find the spring constant in the last one, we have to find this constant here. And on the surface of the Earth, now, when I am on the surface of the Earth, the distance between me and the center of the Earth is not 0. So when it says it weighs 10 metric tons on the surface of the Earth, that means it's that much force when they are 4,000 miles away. That metric ton satellite, that satellite is 4,000 miles away from the center of the Earth. So the distance between them is 4,000 miles. It weighs 10 metric tons. That's the amount of force on it. And now we can find C. So that constant, I'm not going to simplify it because I don't want to write scientific notation, so I'll just leave it as 4,000 squared times 10. That would be my constant. So the force function I have on the surface of the Earth would be 4,000 squared times 10 over x squared. 4,000 squared times 10 over x squared. So that constant in the numerator over x squared. Now, we're not ejecting this satellite on the surface of the Earth. If it was, then we use this as our force function and integrate this over the distance we are propelling it into orbit. We are sending this into orbit over the moon. That's where now the gravity comes into effect. This tells me the relationship between these forces. So while this is the force on Earth, if we want to know the force on the moon, remember it's 1/6 of that gravity. So actually the force function we are concerned with is 1/6 of this number. This would be the amount of force on the moon. So it's 1/6 of that. It's just scaled by 1/6. Why do I not care to distribute all these constants out? Because remember, when it comes to integration, constants can be pulled out of integrals, so I don't really care to simplify them right now. I'll leave them as is until the end. And now that we have our force function on the moon, all we need to do is integrate this force function over the distance traveled, or the distance in this case between the two objects. And so the amount of work done is the definite integral of this force function. It's a lot of constants. Don't worry about all the constants. The only variable is the x squared in the bottom. And I integrate this force function over the distance between the objects. Now, be careful. We are sending this satellite 100 miles above the surface of the moon. It would be incorrect to put 0 to 100 here as my bounds. And that's again because we're not starting the satellite at the center of the moon. We are ejecting it from the surface of the moon 100 miles above the surface. And so that means the lower bound of integration, I am already starting at 1,000 miles away from the center of the moon. The radius of the moon is 1,000. That's what we're using here. And then to send it 100 miles above the surface now gives me an upper limit of 1,100. So to send this satellite 100 miles above the surface of the moon, my lower bound, they are starting out 1,000 miles away from each other and ending 1,100 miles away from each other. And that's again because the satellite isn't starting at the center of the moon, it's starting 1,000 miles away on the surface of the moon, and therefore ending at 1,100 miles away. Now, although this is a lot of constants, remember that when we calculate definite integrals, constants can be pulled out of integrals, so I'm just going to pull that big number out. It's 10. And then we need to integrate from 1,000 to 1,100, 1 over x squared dx. So that big number can just be factored out. We need the antiderivative of 1 over x squared. which if we use our power rule, right, x is x to the negative 2 gives me negative 1 over x, x to the negative 1 over negative 1, evaluate from 1,000 to 1,100. And so what do we end up getting? 4,000 squared times 10. And of course, I probably want a calculator at this point. Plugging my upper limit, negative 1 over 1,100 minus negative, so minus makes plus 1 over 1,000. Plug in the upper limit, negative 1 over 1,100, and then minus negative 1 over 1,000, or plus then. And I would get a calculator out and find this number to put it in and round it off to a certain decimal place or whatever, or certain hundreds of miles that they're asking. But the point is, this is the number that we get. This is the value or the amount of work done. And in this case, my answer is, non-standard at all, metric ton miles. Not a standard unit, but a unit of work nonetheless. And the idea is we're not as concerned with standard units because, again, we're more concerned with the calculus behind it. So springs and gravity are nice examples of very specific force functions that we can use and just get kind of our hands on an application of integration outside the world of geometry and volume and arc length and surface area, and see it in physics, for example, in terms of work. We see integration come up. All right, so we'll end here in chapter 7. And what we're going to do next is we're going to move forward into the next chapter in the book. And the next chapter now addresses all of the other techniques of integration that we have available. And so at this point, we need to know a little more about integration. Integration comes up a lot. We're going to need some more techniques because at this point, we can't answer all types of integrals yet. We're going to need some new properties, some new tools in order to evaluate more complicated and more intricate types of integrals that are going to be set up for us. So next discussion, we'll move into chapter 8, and we will begin our first technique of integration. So other than that, I will be talking to you guys soon.